This is notes 2-4. We're going into writing proofs. It's very basic. You've seen this already in Algebra 1, what we're doing this time, but we're going to explain a few more things. You might want to try this and pause the video. Make sure you can get this before you move on. All right, so this is invalid. The Q, see, it should be a P right there, not a Q. And it makes sense because it could be wet from the sprinklers and not just the rain. Okay, so postulate, theorem, and proof are the words that we need to know. A postulate is a statement that's accepted. You don't need any proof. It's just like, you know, it's obvious. Like a, I don't know, like a point is between two lines, or between 2 points. The definition of betweenness. There are just some statements that just are taken as fact. Theorem is something that's proven. You have to prove it with other conjectures and theorems. A proof is a logical argument that people accept the truth after you prove it. So tell me why this happened. Explain to me. Prove it to me that it works this way. So we're going to use deductive reasoning. It uses this process of it. These are postulates. So here's some better examples from what I was trying to mumble before. Through any 2 points, there's exactly one line. That's a given thing. That's the way it is. Through any 3 non-collinear points, there's exactly one plane. So we've talked about these. These sound familiar. This is why I wanted you to know that first unit so well, because it's coming back to us. So 2-3, a line contains at least 2 points. We've heard that before. A plane contains at least 3 non-collinear points. So 3 non-collinear points makes a plane. And then if 2 points lie in a plane, then the entire line containing those points lies in the plane. We've talked about being contained on the plane before. Some more are if 2 lines intersect, then their intersection is exactly 1 point. We've heard that before. And then where 2 planes crosses and the intersection is a line. These have numbers beside them, and this is only for reference from the book. If you go to a different book or a different country or a different anything, the numbers won't match up exactly necessarily. It might be 5.2, chapter 5, section 2 from some other book. So don't use the numbers with these. You just write out the description of them if you have to give a reason. So we're going to state the postulates can be used to show that the statement is true. Points F and E determine a line. So we go back up to the list. Points F and E determine a line. Let's see. So through any 2 points, there's exactly one line. So what we would do is come down here and we would write through any 2 points. And you can abbreviate. There is exactly one line. The thing about abbreviations, though, if they have to be specifically to that. So points is a pretty well accepted abbreviation for points, or PTS is. Okay, so you guys try to do this one, and this one. You're going to use the lists that are up here. So all of these. Pause the video and try it. So for B, if 2 points lie in a plane, then the entire line is contained on that plane. So here's points A and D. And A and D lie in plane A, B, C, and on line N. So line N lies entirely in plane A, B, and C. Okay, next one, there's a plane that contains F, A, and B. Now there's 2 that could fit this. This one is the better one because we're talking about containing. So the one that uses the word containing is through. Okay, I'm going to correct myself on this one. This one could be confused with the other one, which is, it says a plane contains at least 3 non-collinear points. So a plane contains at least 3 non-collinear points. So again, we come to the contain words. A plane contains at least 3 points. There is a plane that contains points F, A, and B. If you look, here's A, B, and F. Those are non-collinear. So we're not proving that there's a plane. We're proving that the plane contains those points. And then on D, A, B, and AD intersect at point A. If two lines intersect, then their intersection is exactly 1 point. Next, we come to the always, sometimes, never. Always means that there's no counterexample that will work. There's never a counterexample. It always is true. Sometimes means that even though it might be true, there might be a counterexample. So you need to prove that these are not true. Never true means it's an impossibility. So you have to decide on these whether they're always, sometimes, or never true. And we're going to use those postulates to decide. So you go and decide. Follow the postulates, see if you can figure it out. The postulate above says that the intersection of two planes is a line. Well, the intersection of three planes could be a line. So here's my three planes. If I draw these going out like that with these lines being parallel, my line that goes in the middle, I could have something like this. And that could work. But all it takes to be sometimes is 2, so this could be true. But to make it sometimes, you have to find one counterexample that makes it non-true. So what if I drew my three planes like this? Oops. So for something like this, the statement is true. But there are three lines that are the intersection of those three planes. So this would be sometimes. So it could be true here, but this is our counterexample to counteract the always. Okay, the next one, through points H and K, there is exactly one line. Okay, so here's H, here's K. No matter where I draw them, it's always true. And the reason why is between any 2 points, is exactly one line. Okay, plane A and B intersect in exactly 1 point. This one is never true. It doesn't happen. They never intersect in 1 point. It's always a line. So that's the always, sometimes, never game. Remember, sometimes it's true, but there might be a case where it's not, and it just takes one not true, one false to make it sometimes. Always means it always is 100% of the time. Never means not a thing. The proof process goes like this. We have a given statement. We have statements and reasons, and then we have the final proof, the conclusion. We never use the word prove in our thing or conclusion, but that's just a description of what these are. And I say that because some of you are going to try to write prove at the end. So for example, we want to prove that M is the midpoint of AB, that if M is the midpoint of AB, so that would be our given information. M is the midpoint. And I'm going to write midpoint like that of AB. The reason why is that's given. So we have to prove that if M is a midpoint, let's draw a picture because that helps too. M is the midpoint. Then AM equals MB. And you go, wait a minute, Mrs. Chris, or they're congruent. You go, wait a minute, Mrs. Chris, you told us that's true, so it has to be. So we're going to use some logical steps. The next step with this, using our definitions that we've talked about, there are some definitions I'm going to ask you to pull together. In fact, you can see in your OneNote, there's some fill-in sections in here. The definitions. These are definitions. They are highlighted in yellow in your book. And they are throughout the chapters that we have gone through before. So you're going to need to fill these in. I have a key that you can check with and make sure you've got them all eventually, but for right now I want you to try to fill them in. You can either type the definitions in there or you can pull this out and then you can write the definitions in there. It's up to you. But I want you to fill these out. There also are some for the postulates and the theorems and the properties. Okay, so back to our lesson. So using the definitions that we know that AM equals MB The reason why is a definition of the midpoint. And we also know, because of that, the AM is congruent to MB by the definition of congruency. Now, we're not going to go into those details right now. We're going to do this simpler, but I wanted to introduce a proof process to you so you could see this. So by the definition of congruency, so notice that I changed from the measure version of the line segments to the congruent version, and that happens because of this. So what that brings us to is the midpoint theorem. So we have just proved the midpoint theorem. If M is the midpoint of AB, then AM, line segment AM, is congruent to line segment MB. And then we can say the measure is the same. Here are some properties you've already talked about in algebra. The addition property of equality says that if you add to one side, you add to the other. Subtraction says if you subtract from one side, subtract from the other. We've got multiplication, division. Reflexive is probably new. Reflexive just means that something equals itself. It's not reflective, so it's not flect. It's reflexive, so it has to do with equaling itself. Symmetric is what you might think of as reflective. So this is the reflective one. Notice that if A equals B, then you can say B equals A. Transitive follows our syllogism process that we just talked about. If A equals B and B equals C, then A equals C. Okay, so that's following that PQQR process. Substitution just means you can substitute for something, one thing for another. So 4 times 2, if I use a substitution property, it equals 8. Distributive we've used before too. So you're going to identify the property that justifies these statements. I'll help you with the first one. The first one, I changed this to be 4x plus 5. It looks like it might be distributive, right? But what's different is the 3 is gone. How did I do that? I divided by 3 to get to that. So this would be division property of equality. You could write it like that. Okay, you try the next ones. All right, check that you did this. So the symmetric property of equality, the only difference between these is they're switched. This one, we subtracted 25 from both sides. This one looks like it might be distributive or transitive maybe, but then look at it. Everything is the same here and here, but the 2x minus 1 is what used to be just y. So that's substitution. And then this one, if I set it up vertically, if P then Q, if Q then R, if P or P equals R. So this is like our transitive one. So we're going to prove that this is equal to x equals -4. And we're going to go into a second video, so it'll be just a couple minutes for the second video. But I'm running out of my 15-minute limit on here, so I'll go quickly, but we'll get this. Okay, so if I'm just solving this, I'm going to do this, distribute, right? So 2x plus 14 equals 6. So what I've done is I've used distributive property. This is what you did in Algebra 1. Okay, then I'm going to take away 14 from both sides. So this is now 2x equals -8. How did that happen? Subtraction. Subtraction property of equality. Well, this is just distributive, sorry, not property. Okay, and then we divide by 2. So this is now x equals -4. How did that happen? Division, property of equality. I want you to notice that the reason why, so this is the given, then how I got from here to here is right there. How I got from here to here, the reason is there. The reason I got from here to here is right there. Okay? All right, next video, pick up on this.